Our last topic for NMR will be something called spin-spin splitting or multiplicity, and that is you've noticed that these peaks are not just one peak usually. They could be one peak or they could be 3 peaks clustered together, 4 peaks clustered together. So these different patterns, that gives me even more information about those hydrogens. What that is a multiplicity. Each signal could be a different pattern. Now these are the patterns that we usually see: singlet, doublet, where they're equal lengths or heights; triplet, we have a short, long, short; quartet, short, long, long, short; quintet, short, long, longer, long, short. Okay, anyway, you get the point. There are so many peaks at this point that we just call it a multiplet. Okay, so just an M for multiplet. So Q will be quartet, T will be triplet, D will be doublet, S will be singlet. So what do we have up here? We have a 1, 2, 3, 4. We have a quartet, and we've got a 1, 2, 3 triplet. Now, noting the pattern of long and short is really important, because if I saw something like, I don't know, if I saw something like this, you know, I would sort of know that, oh wait, this is a triplet, but a quartet is not supposed to look like this. A quartet is supposed to look like short, long, long, short. That tells me that this might be another signal, and this is this is a different signal, and they're sort of close to each other. So that kind of information is really important. Now, they're not going to be perfectly aligned. Like this and this are not always exactly the same. The doublet is not exactly the same. One might be slightly higher. So don't worry too much about that, but just know approximately the shape, the profile of these curves. So where do those splits come from? Okay, so splitting is what causes singlets to turn into doublets, to turn into triplets or quartets. The splitting is what's causing, you know, the multiple peaks. Okay, because the way I think about it is, this thing is supposed to be one signal because it's the same equivalent hydrogens. You know, these are equivalent to each other. But because of hydrogens nearby, they are going to interact with these in a way that splits it into multiple signals. Okay, so that's why I see multiple peaks. So the way that works, just briefly and really simply, is let's say that we have a signal for HA. So we're looking at a signal for HA. Well, HB is nearby, and technically it's usually within 3 sigma bonds. So let's count 1, 2, 3. Yeah, within 3 sigma bonds, we see the splitting effect. So first you want to make sure that it's close enough to have an effect. The second thing is, when this splits the signal, there are 2 orientations for HB. There's against the field or with the field compared to the external magnetic. So those 2 orientations are going to cause either an additive effect, so you're going to see part of the peak at a higher, more de-shielded region, or a subtractive effect. So this takes away from that, so you feel more shielded. So because both of these are equally possible, you're going to see these peaks be the same height. More simple way that I think of it is, I don't even think about this so much. I just think this hydrogen is going to split this signal by 1 because there's only 1 hydrogen there. And so what I do is I picture the signal as this HA would give a signal, and then any hydrogens nearby are going to split that signal. So if I have 1 hydrogen nearby, it's going to split that signal once. And when it splits it down in half, then this is going to turn into that, because the split occurred right here. Okay, so that's from HB splitting the signal for HA. So that's how I think of the doublet occurring. Different scenario, let's say we have 2 HB atoms now. So before we just had 1, and now we have 2, and they're both within 3 sigma bonds. Okay, so they're both going to split HA. And you can also think of this rotating, so they both have access to HA. And they're both equivalent to each other. You can't tell the difference between which HB is splitting HA. So again, the field description is both HBs could have a spin, their induced field going this way, against the external field, so that has a subtractive effect. We could see that those might be additive. They might both be going in the same direction as the external field, or some, it could be some combination. Maybe this one is up and this one is down, or reverse. So because you have these different possibilities, you've got the most downfield ones, you've got the ones in the middle, and you've got the most upfield ones. So that's where these three peaks come from. Again, my really simple way of thinking about it is, here's HA's signal, just one signal, and then you have HB over here splitting that signal, and you have this HB here splitting that signal. So you're going to end up with a short, a long, and a short. And that's what we see with the triplet. And then this brings up something that is really helpful, which is that notice that however many splits that I make, one split, I end up with two peaks. If I make two splits, I end up with three peaks. So that is what we call the N+1 rule, which is down here. N+1 rule tells me that however many hydrogens are nearby, if I add one, I get the number of peaks. So let's try that here. HA gives me peak, but HB here maybe splits it. This one splits it also, and this one splits it also. So three splits means I'm going to have short, long, long, short. I'm going to have four peaks. So three neighbors, and then I add one because it's N+1. So that's going to be 4. And this is the number of peaks I get, or number of, this is the splitting pattern, also called the multiplicity. And 3 is the number of neighboring hydrogens within 3 bonds. All right, so a few other things to note. These equivalent hydrogens don't split each other. So notice we didn't have HB signal here split by another HB because they all overlap with each other. So the idea here is, let's look at HB signal now. HB will have a signal, and this HB will have a signal that's the same as this HB. They basically will overlap on top of each other. They're the same thing. So they're equivalent to each other. They have one signal for all of them. All right, so you can think of it as this signal is here. This one signal is also on top of this one, and this signal over here is on top of this one. Yeah, that's one way to think about it. So what will be the multiplicity of this peak, knowing that there's only HA next door? Well, you can think of it as HA splits this signal, and there's only one neighbor, so it's going to be a doublet. Or you can say N+1, you have one neighbor HA, plus 1 equals 2. It'll be a doublet. So either way is fine. Here we see these are equivalent, so you're just going to get one signal, and they won't split each other, so this is what we call a singlet. Splitting is generally observed within 3 sigma bonds, so usually we would not say HB would split HA. So these will be a singlet and a singlet because they will not be close enough to each other to observe splitting. But if a molecule is long enough, sometimes you can see effects of splitting, what we call long-range splitting, when you have possibilities for hydrogens to get close to each other. So these splitting patterns come from something called Pascal's triangle. And you guys can see this sort of mathematical thing. It's sort of cool, like 1, and then you have 1 and 1, and these 2 add up to 2, and 2 and 1 add up to 3, and 3 and 1 add up to 4, 4 and 1 add up to 5, 4 and 6 add up to 10. So you can use these little this little mathematical pattern to construct this pyramid that's really cool, but it also gives you the ratios. So it comes from the probability, and you can tell this is based on probability, right? All the different orientations. You can see one possibility here, 2 possibilities that are equivalent are twice as big, then one possibility here again. So this gives us that ratio of 1 to 2 to 1, and you can go through, and it all has to do with those spins. You just have to work through the probability. Spins can be the same, they can be opposite. You can work through it with 3. You know, how would this look if you had 3 different spins, 3 different hydrogens to consider? So it just gets bigger and bigger, but I usually don't focus on it, but I just think it's pretty cool. So now let's look at these patterns here, and let's see if we can figure out the multiplicity based on these structures. Let's do one together. So we have A. We have CH3 here. Again, if you feel more comfortable drawing out the H's so you can see them and know about them, that I really recommend that. I don't always do that now, but I should because I think it's really helpful. At least draw them out. You see them. You see how many bonds are they to the next nearest hydrogen, which is way over here. So 1, 2, 3, 4. So these hydrogens are attached here. So 4 sigma bonds is not enough to observe splitting. So this will be a singlet over here. These two also are too far away from these, so these will be a singlet. These are close enough to here, so 1, 2, 3. So they're within 3 bonds. So this one will be split by its 3 equivalent neighbors. So 3 plus 1 is 4. So this is going to be a quartet. This one is split by its neighbors. 2 neighbors plus 1 is a triplet. All right, so that is what I would expect to see for the splitting pattern. And then I would work on placing those patterns along the chemical shift based on what kind of functional groups are nearby. After that, you have an NMR spectrum. So go ahead and try B, C, and D. Okay guys, so for this one, this is far away from here, just like we saw up here. These two are singlets. This is a multiplet. Don't forget there's a hydrogen right here. This guy right here. That hydrogen sees 7 or 6 non-equivalent 6 equivalent hydrogens. These 2 methyl group hydrogens are the same, equivalent. So 6 plus 1 is 7, so you'd see a multiplet. And then these 2 methyl groups are equivalent to each other, so we'd see a doublet for those. Singlet, 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 singlet. And these are all equivalent to each other, so 1 singlet for all these methyls and 1 singlet for both of these methyls. The hydrogens here are too far away from here. 1, 2, 3, 4. And these hydrogens here, 1, 2, 3, 4. They're too far away. So these are all singlets. I'd see 4 singlets for this one. And this last one here, I see a triplet because that's 2 neighbors plus 1. These 2 neighbors have 3 neighbors, so 3 plus 1 is a quartet for this guy. The hydrogen right here sees 3 equivalent hydrogens from the methyl, so that's a quartet. This methyl group is 3 hydrogens, but we see 1 neighbor here. So that 1 neighbor means that this signal is going to be a doublet. And here we see a quartet and a triplet. But notice the equivalency here. So we have symmetry right here. And so it turns out that these are replicated. These are actually equivalent to these over here. So, I would only see 1, 2, 3, 4 signals. Now notice some of the patterns. This ethyl group here gave me a quartet and a triplet. This ethyl group here gave me a quartet and a triplet because you have CH3CH2. That's an ethyl group. So it's usually going to give you a quartet and a triplet. So here's a common pattern, ethyl group. You can tell when there's a quartet and a triplet that sometimes that's going to be because of, usually that's going to be because of an ethyl group. And usually it's the quartet, the CH2 group is usually attached to something that causes it to be more downfield. So sometimes you see the quartet first and then the triplet. Isopropyl will be, I think you guys can see that pattern here. Here's an isopropyl group. So we see a doublet from the methyl groups because they're split by the 1 hydrogen here. And then you see the multiplet because they're split by all the methyl group hydrogens. So here's that multiplet here, and that's usually the one that's attached to something, so that's more downfield usually. And then the hydrogen on the outside, the ones farthest away from the attachment point, is more upfield, and those are the 6H. Whenever you see 3H, it's usually due to a methyl group. When you see 6H, it could be from 2 methyl groups, or it could be from 3 CH2 groups as well, but usually it's going to be methyl groups. You just have to look at the molecule and see. So isopropyl is another pattern to be familiar with, is a doublet at 6H integration and a multiplet 1H integration nearby. And then our last example that's very common is the Tert-Butyl pattern. Tert-Butyl groups, I think we've seen up here. Tert-Butyl is going to be equivalent hydrogens to each other, but pretty far away from other hydrogens that the tert-butyl group could be attached to. Therefore, there's no splitting. So you're going to get a 9H, which tells you 3 CH3s, and it's going to be a singlet. So these are really good patterns to sort of keep in your back pocket when you look at NMRs. And again, here is some information about that isopropyl pattern, the 1H and the 6H. What's going on here? The 6H here don't split each other because they're equivalent, but they're split by the one neighbor. So that's why this is a doublet here. This H gives a signal that's split by its 6 neighbors that are equivalent. So that's why we see this complex multiplet. It should be 7, 1, 2, 3, 4, 5, 6, 7. But we would just call it a multiplet for short. Doublet and a multiplet. And we call it geminal because these are like twins. It's a geminal dimethyl group. So let's do a practice problem, 15.17. Here are some NMRs with their integrations on top. See if you can figure out whether they contain any of those groups and patterns that we talked about above. And then see if you can think based on its chemical formula, is there a certain structure that could work for this? So let's do one of these together. I'm looking at this 6H and I'm thinking it's got 2 CH3 groups. So, and they're equivalent to each other, so there's going to be some symmetry. And I see this multiplet here. So maybe this is too easy because we just did an example like that, but I could sort of piece that together also without knowing about that. I just know there's 2 equivalent methyl groups and there's a hydrogen within 3 bonds. So that tells me that I have that. And they blew this up, so 1, 2, 3, 4, 5, 6, 7. You could tell there's 6 neighbors here because there's 7 peaks. So that tells me that these are close to each other, splitting each other. And then I have this 5H integration between 7 and 8. And here's where we need to use our knowledge of chemical shift. What kind of functional group is between 7 and 8 for its chemical shift? So if you guys look back at the chart we made together, 7 to 8 is a hydrogen on benzene rings. So it's the phenyl hydrogens. So that means I have a phenyl group. 5H means that I have monosubstitution, meaning there's one group on the benzene ring, one R group. So these 5 H's here tell me I have one spot that's connected to some other stuff. I know I have this dimethyl group, and so there we go. And then I just check, is it C9H12? So here's 6, 7, 8, 9. All right, so see if you guys can do that. Identify some patterns that you just learned. See if you can put the shift together with the splitting and the chemical formula, and see if you can come up with a plausible structure that fits all that information. It's like playing chemical detective. And then continue and do these as well, and for this one you have to figure out the integration. Now for this one, part B, I see, wow, I see a lot of stuff here. First might want to look at this and just get a sense of how many degrees of unsaturation there are, just to see are there pi bonds and things like that. So 6 carbons, 1, 2, 3, 4, 5, 6. I usually just draw a hypothetical version of this molecule with no pi bonds in it, and I use up everything that I have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that leaves me with 2 spots without hydrogen that should have hydrogens there. 2 spots divided by 2 is 1. So I see there's 1 degree of unsaturation. That tells me that there's a pi bond in here somewhere. The other possibility is there's 1 ring. So I either have a pi bond or a ring. Now the fact that I see a signal between 2 and 3, if you recall, that could be from a carbonyl alpha hydrogen. Okay, so I'm going to keep that in mind. And I know there's 2 such alpha hydrogens. I also see a triplet and a doublet here. So that might tell me something. 6H here tells me it might be 2 methyl groups with 1 neighbor nearby. And then this one here tells me that I might have a CH3 with 2 neighbors nearby. Now here are those 2 neighbors, and this one's a quartet. This one's a triplet. Do you guys remember that pattern? I have a triplet and a quartet. All right, and they're integrated 2 and 3, or 3 and 2 respectively. So that goes back to one of my patterns, 3H and a 2H triplet quartet. So that's telling me that I probably have an ethyl group where the CH2 group is close to a carbonyl group. So already I can piece together an ethyl group next to a carbonyl. All right, so that tells me half of the molecule, and now I just need to figure out the other half. Now a 6 doublet, 6H integration, and then a multiplet would tell me that I have this geminal dimethyl going on. However, this is way downfield. It's at 5 as opposed to being, down here usually it's just an alkyl. If it's an alkyl group, it shouldn't be as high. So that's telling me that this 1H is really close to something electronegative. And if you notice, I have 2 oxygens. So I probably have another oxygen. And then I've got my isopropyl group. So what's going on here is that this H, even though it should be between 3 and 4 because it's next to an O, there's this greater de-shielding effect that's causing it to be downfield even more. And that's because of maybe potentially resonance from this ester group as opposed to just an oxygen by itself. So this hydrogen's feeling even more de-shielded than usual because of this resonance. And then we've got CH3 from these doublets over here. So this molecule fits the C6H12O2, and if I want to assign the peaks, let's call this A, B, C, and D, and this D is equivalent to that D. So let's sort of clear the air here. If I have A, B, C, D hydrogens, then I have A is that triplet right here. B is the CH2 of the ethyl group. Hydrogen C is the 1H way down here. And my doublet is due to these 2 geminal dimethyl groups over here. All right, so A, B, C, and D corresponding to these hydrogens. All right, so on this one, first we have to divide everything by 6 to get the integration. So this is going to be a 1H hydrogen. This is going to be 2H, 2H, and then this is 9H over here. So I think you guys see that 9H corresponds to one of our patterns, and that is the Tert-Butyl pattern. 9H is 3 methyl groups, and they're all equivalent, so they don't split each other, which is why we see a singlet. So here we're going to see 1, 2, 3, some kind of Tert-Butyl group. And then I see a 1H group here, and see how it's sort of broad, and so that tells me I probably have some kind of that together with the formula tells me I probably have some kind of an OH group. And then the fact that I have stuff between 7 and 8 tells me I have a benzene ring. And then this pattern is sort of common, which is, it looks like a quartet, but it's sort of split. And that's due to substitution pattern where we have 2H and 2H, usually like this, a 1,4 substitution pattern, disubstitution. And when you have 2 different groups here, let's say X and Y, then the symmetry of this is like that. And so you're going to get the 2 equivalent hydrogens here and 2 equivalent hydrogens over here. And the thing is, their neighbors are going to split. So this blue hydrogen will split the signal for the green hydrogen into a doublet, and the green hydrogen will split the blue one into a doublet. So you see this pattern here as a result, which is called a doublet of doublets. It's a doublet within a doublet. Okay, so I think we can get it from here because we have 10 carbons. I don't even have to do degree of unsaturation. I know I have a benzene ring, so I'm going to go ahead and start with that. And I know I've got this Tert-Butyl group, 1, 2, 3, 4. So 4 carbons plus 6 carbons is 10 carbons. And then I know I have an OH group. And if I just count all my hydrogens just to make sure, 4 hydrogens in the ring, and then I've got 9 hydrogens here, then I only have 1 hydrogen left. There you go. Sometimes that just works out really easily. Now for this last one, I'm going to use integration to tell that there's no methyl groups. And I know that this 5H between 7 and 8 using chemical shift tells me that I have a benzene ring that's mono-substituted because I have 5 H's. So I know I have something like that. These guys are most likely to be CH2 groups. And this one here, this is really suspicious. I wonder what that's all about. So there's only a 1 H integration for a singlet. So just using the fact that we have C8, so I just have 2 more carbons after this. And I know that I have CH2 groups. And they're next to each other because they're triplets, so they have 2 neighbors. So CH2 is a neighbor of CH2. And then I know I have an O. So I'm just going to count. This is 5 H's here, 6, 7, 8, 9, and that really just leaves my oxygen and then 1 H, 10. So that all works out. So C10, C8, H10, O. And so this singlet here is variable because it's that exchangeable hydrogen. So this is my OH hydrogen, and it's a singlet. Okay, so these are like little mini puzzles where you got to put the clues together. Notice how I sort of jumbled it up, but you could go, if you want to be systematic, maybe just think about the integrations and then think about the chemical shifts and then think about the splitting. You could go in that order and then piece it together. I usually find it useful to just write the pieces. This peak gives me this piece. This peak gives me this piece. This peak gives me that piece. And then try to piece them together. But it's really up to you how you want to solve them. But just thinking about all those things, though, is how you're going to get the answer. You have to think about splitting. You have to think about chemical shift. Integration is very helpful. Not always necessary, but really helpful. So put all those concepts together and just do as much practice as you can.